Last week we were seeing finite difference and using them for the advection equation, namely the one-dimensional wave equation. So I'm going to continue. I made a new notebook for this, so we'll go through this again with some more details and things. So the idea here is that you could do the lab using some of these things and understanding things in the way that they're in the lab. So we want to solve the wave equation using the method of lines and finite difference. The method of line is simply that you first discretize in space, and so you get a system which is continuing in time and discrete in space. You analyze that system, and then at the end, if the system has good properties, then you discretize in time using the ordinary differential equations method that we saw before, namely Runge-Kutta. So we'll start. So we want to solve this equation here. Let me see if I can use the pen. It's better. So we want to solve this equation. Do you see the mark that I'm doing or no? You see the red thing or yours? Because here I don't see. I think I have to change this. Okay, sorry. I have to change in the Zoom what I'm. So I will have to put the whole. Okay, now. Okay, so now you see the red one. Okay, so we are going to solve this equation, and we are going to put an initial data, which is very appropriate to check the properties of the solution. And this is a data which is of compact support, so is zero outside some region, and then is a polynomial here. So here is not perfectly smooth, but there is a jump in some derivative. We typically were going to use here this p equals to 8 or 4, between 4 and 8. So this thing has, say, 7 derivatives, which are okay, and then there is a jump in one of the derivatives. So if you take higher derivatives, then here you get 0, and then you get something. But this is the 8th or 9th derivative, so it's for the numerical method, they are going to be contained on the error. Why we use this? Because if you put some exponential or some sign or something, and for this since we are going to take omega equal to 0, so this is just a 1. If you take these functions, you know the differentiability, you control it. If you take a sign or something on exponential, then you don't know, because those are done those are computed in the computer by some series, Taylor series in some places or other developments, and they are not smooth across some boundaries, so that you don't know. So it's better not to use them. So our data will be in principle like this, and later we are going to put here a wave, a very high frequency wave inside. That's why we are putting the cosine. And then we are also going to treat a case like this, where you have a wave going like this, a small perturbation. So these are the cases we are going to see. So we define the data, the initial data, this way, and we can plot it. And here you have the plot. And here you see we are using p here to the order 8th. We could use 4 also, no problem. And we are using periodic boundary conditions, so we will connect this side with this side. So this point here, I cannot mark over these things. This point here is the same as this point. So here we have a plot on how it's going to evolve. And you see we'll start here. It will start here. This is the initial data. I'm going to move to the left. So after one period, it's going to be on the other side. Here I'm moving the solution on raising it so that you can see like if we're a 3D plot. For that we are just adding to the X this correction, and we are moving it to in the vertical direction with this alpha. Okay, just to draw it in a nice way. So as I say, we are going to use the method of lines, and that means that we are going to take some points. Here I put the points. Xi is x naught plus dx times y minus 1, and I goes between 1 and big N. And so we have agreed that is equi-space, and the x is L over N, where L is this distance. So I want that when I is equal to N plus 1, I will be in the position L. So if I is N plus 1, this is N, so I have to divide by N and multiply by L to get L, so dx is L over N, right? So those points we will represent the approximate solution by points along at these points, and I'm going to call them BI. So in the back of our mind we are going to have that we are solving for this, but we really are solving for these quantities. So it's a vector that depends on time. And we shall use a finite difference operator, dx. So that we'll get an equation which is discrete in space, but is continuous in time. This way we are going to get an ordinary differential equation in time, and then we are going to solve the ordinary differential equation. So in the end we are going to get this system, right? A is is the speed of the wave. We generally we are going to take either to be 1 or -1 according to what we want, either to move to the right or to the left. So now we introduce again the finite difference operators. So we have this grid. Here I just say the same as above. We have some smooth function here, and we discretize it, so we have the points. And really here you can think of these points, this blue thing, as a v twiddle t of x. Some function interpolating the real points. These are the points p t of I, p I of t, sorry. And this is interpolation. And so this in blue will be the approximation to our solution, will be u of tx. That we know is how, if we start with some data like that, it's going to move toward the left with a equal to 1, with velocity 1, okay? I think here I have a grid. So once we do that, when we solve for the problem in space and time using an ordinary differential equation solver, we are going to have this point, and we are going to evolve in time. So there will be a dt here, a dx here, or sometimes I go just dx here, and this is going to be dt. And so we are going to march in time and having a discretization in space and time. And of course in time we are also do some interpolation to get this thing out of bi of t, which comes from bni. These are the values here. So with the I moves in the space direction, the n moves in the time direction. Okay. So this is, if this is n, this is n plus 1, and if this is point is I, this is I minus 1, etc. And here we are not putting this point here, because since we are using periodic boundary conditions, this point here is the same as this point here. Okay? Questions? This is very, I guess, by now everybody knows this. So we saw the simplest finite difference operators. You can do the definition of the derivative will be the limit of one of these things going for the x going to infinity, but we can take any one of them. So we take either, if we are at the point I, we take either this difference. This is a plus derivative of plus the finite difference, or we can take this difference, and this is the minus finite difference. So to see what is the error we are making, we can do Taylor series expansion of u, assuming that u is sufficiently smooth, and then you can check that this thing is just the derivative of the point plus some error that goes like x. So this is the first term, and these are higher terms. But this is important. So we have an error that goes like the second derivative times dx. But notice that if we define the average of these two things, then this part cancels out, and you have that the error now is dx squared. So this is a better approximation. And in general, for points where we have the right and left points, say if we have these 2 points, so this is the best way. So we usually do this. These are called centered difference operators. And notice that this, for instance, the error here for the second order polynomials, so something like a plus bx plus cx squared, is exact, right? Because the error has the third derivative of u, and the third derivative of u for this polynomial is 0. So one way of checking things or finding this approximation is applying them to polynomials. For instance, if we have, notice how it is. If you have some finite difference operator, let me call it D8, so that is 8 times differential. The error goes like delta x to the 8th, so the error has to go like the 8th derivative times the 9th derivative, sorry. The 9th, I'm going to write it here. If we have an operator which is 8th order accurate, then the error will go like the 9th derivative times something here times delta x to the 8th. Why is that? Because we have to have the dimensions right. So if we take, this has dimensions of u over length, and so this part to have a dimension of u over length in the Taylor expansion has to be this term. So that says that this thing is precise to polynomials of order 8. So if you apply d8 of the polynomial of order 8, this is the same way as the dpa dx8 dx, okay? So this is exact. So one way of finding the higher order approximation is just to apply to polynomials. That we saw that also. So, and in fact, we can have these high accuracy operators by just, for instance, for the D4, we say, okay, we will take a centered stencil with 2 points on each side and with some constant here that we have to find out, and we apply it to polynomials, to linear polynomials here and to cubic polynomials, which are 0 at the point I. So they are these two. And then you see that with these two equations you get the coefficients, and this is the fourth order derivative. So in the circle we can use just these operators because in the circle with periodic boundary conditions, so we know that we have available always the, if I am the one in the point 1, I will use the point 2, and here it will be the same point as the end point. So this side is the point n. So the point, really the point at the extreme, we don't use it because it's the same as the 1. So the end point is this one here. So and if we are going to use the fourth order method, we just use this 4 and minus 1. Okay. So for the periodic boundary conditions, we can use these stencils all over the place. And here are the matrices for the plus and the 0. And you notice that this metric is not antisymmetric, but this metric is antisymmetric. So we saw that that imply that the D node has purely imaginary eigenvalues. And this is because if we take a scalar product like this, so U bar times B, there shouldn't be any comma here. Let's correct this right now. If we take this as scalar product, then we see that this in here is minus this. So I times D0 can go to the other side because you have the complex conjugate here. So this is the same as this. So this operator, D0 is Hermitian, and so the values of the ID0 are real, and therefore the values of D0 are purely imaginary. So now we go to solve the system. So for using Runge-Kutta, say, we have to put the system in this way. Right, where A is the parameter of the equation, and P is some other parameters that we want to put. Doesn't matter, but we want to put in this way, so we have to produce the function f. So here we first create the derivatives, the finite difference approximations. For that is convenient, but that we use these libraries, bounded matrices. The bounded matrices allows us to say, okay, what is tridiagonal matrix, linear algebra for doing this algebra, and sparse array. Sparse array, what it does is to whenever there is a 0 in the matrix, just take notice at where are the zeros and rearrange the matrix so that you really don't use memory for the points where you have zeros. And also the operations that you do with the matrix are optimized so that you don't run all over zeros and multiply by 0, but just eliminate this. So this is a sparse library. So with these 3 libraries, we can define first we define a matrix here, which has a minus 1/2, has a 0 here, minus 1/2, and 1/2. So there is a diagonal that is 0, which is this one, and there is an upper one which has 1/2 all over the place, and there is one minus 1/2 here. And then at the end point, the one n is minus 1/2, and in the first one in the end, so in this point here in the top of the matrix is minus 1/2, and here at the beginning is 1/2, and then the rest is this metric. So we put these two values, and then we make it sparse all over. We drop the zeros. Here we take, okay, all the zeros of this I don't want to consider. I want to have something without the zeros. So we change this to be something without the zeros, with less memory usage, and then we divide by dx. So this way we get the operator. Sometimes in the lab, I think we didn't divide by dx, just divide at the end when we use it. Here we just to have it in accordance with another package, I just divide by dx. And here is the creation of the d plus, and here is the d minus. So we run this to create these matrices. And then you can check them. For instance, you create them with the n very small, so that, and the x equal to 1, so that we can see how it is. And for instance, the d minus this one is like this. If you want to say the first one,
Dale.
this is the first one. Okay. And you can check the formula, for instance. You can check that if you do d plus d minus and divide by 2, you get this, and it says that this equality is true. And so now we can create the function, okay? So we have created these two metrics, the three metrics, and we can make the function, and the function will take the place where the f is going to be put, that we call the v. Here we put the v that we give. So this is the vector of data at some time. These are the parameters that can enter in this function, and this is the time. In this case, we don't use the time, and we use two parameters. We give the
Vi lo que fueron pasando ahí al coso, pero no.
Hola. We put the parameter here of the speed, and then we put the finite difference operators. And this is multiplication. So here we multiply d by b times a, and put this in this place. This is a very efficient multiplication operator, which does this thing that it says here. So it's alpha times a times b plus beta, which is 0 in this case, times c, and stores everything.
Dale.
I think it's upstairs.
Dale. Tom. Después, si querés, Alan, bueno, si no, mañana cuando nos juntamos te doy las remeras y ya las tenés.
Okay. So this is
Sí, ya
function
estoy.
f.
Estaba hablando como un pelotudo, estaba muteado. Ay, me voy a traer algo para comer porque estoy cagado de hambre. ¡Ay, Dios! Sí.
Okay, yes. Okay, so we will take, for doing the real calculation, we'll take n equal to 100, L equal to 1, so that's the size of the circle, dx L over n. We are going to put equispace points, so we take points between 0 and we equispace with dx until L minus dx. So here we are taking just to the point before the end, right? So we are doing the first point, this is 1, and so 2, 3, say, 4, and the last point, this one we don't put because this one is the same as this one, right? That's why we take this point here is a distance L minus dx. and this is the distance L. So the last point is there. We create the derivatives. I think we are recording, right? Yeah. And we create the derivative, right? So now we have everything. We have to give the initial data. We have the equation. We have to produce the initial data. So we make a bump between 0.3 and 0.7 with p equal to 8 and frequency 0. And we plot it. So we put the is in B naught, which is initial data. I think I didn't run this. Okay. And we get here. The red ones are the real points, and the line is the interpolation that does the plotting subroutine. So the actual things are the red ones. So we are going to evolve until t equal to 1. Since a is equal to 1 and L is equal to t, we should get that this in here is the same as this in here. So this is the initial data. The solution is just initial data move to the left, a distance t, and so this, since this is periodic in L and t is equal to L, this is the same as the initial data. So the true solution has the same value at t equal to 1 that at t equal to 0. So when we evolve, we can check how close are we by just looking after one period. So now we are going to evolve this, and for that we are going to use this package, this library, ordinary differential equations, that has all the methods you want to use, ever want to use, so we just use it. So we produce three set of parameters for the center difference, for the plus difference, minus difference. We take a delta t which is equal to delta x, so that delta t and delta x is 1. And so you solve these problems. You present these three problems. So the same f, the same b naught, the same interval, but you change the derivatives, the finite difference approximations. And now you use, I don't remember if now you solve. You have the solution and you can plot the solutions. This is the solution with the d naughts. So you look at these numbers, it's pretty bad. So it's unstable. Just after one period is totally unstable. So it's not used. If you run with the minus, you get also, it's even worse, 10 to the 37 here. 39, sorry. And if you run with the plus, not with the minus, no, the plus, you get a nice solution, perfectly nice. We can put here, we can compare with the initial data. Let me do that here. So we do plot x b0 which was the initial data. And we see that one is over the other. So what is going on? This is first order, a method that is first order. I'm using Euler, which is first order. With this I'm getting the exact solution, and with the other two I'm getting something which explodes. So these two are unstable, and the plus is okay. Well, there is an explanation we are going to see later on, but we already saw the other day. The D naught has, and we saw now that the D naught has imaginary eigenvalues, purely imaginary eigenvalues. So we have something like the eigenvalues are here. And the stability region of Euler was here. So these in here are some number, C say times delta t divided by delta x, and we are taking this to be 1, so this is some number. Basically this number is less than 1, less than a, say, the absolute value of a. So this is close to unity. In fact, for this problem is unity, so we are like here, and we have the circle here. So this is unstable. We could make better if we take delta t small, but we never are going to be in the regime where this is stable. And if we take delta x smaller, we will have to take this much, much smaller. So that's why this method is bad for the D naught. Now the D plus, D minus has the eigenvalues with the D minus has, let's use blue. The D minus has some eigenvalues which are moved here. Have a positive real part. So these are worse. The D minus on the other, the D plus on the other hand, has eigenvalues here with some negative real part. So if we make them small enough, they fall into this circle, and that's why we have conversions. Now you will say, okay, but why do you solve this problem exactly? Well, this is because we are solving a very simple problem, and in this problem you can see that the Euler method produced the I don't know whether I put it here, let me check. No. Well, what happens with this is that the Euler thing will tell you that BI n plus 1 minus BI n divided by delta t is equals to BI plus 1 minus BI minus 1 at n over delta x. Right, this is the approximation if you look at Euler. And this is exact. You can check that because a form that has a solution, this is exact. If you put here the u, the solution, you will get that this is exact. So here you are solving the exact problem. That's why you get this. So this is valid for u of tx equals to any function of t plus x. You can check that. So that's why we are getting the right solution. So you might use these methods. Some people use, but then you have to know, if you are having a system, you have to put the system in a diagonal form and check what are the velocities and put the d plus for the positive velocities and d minus for the negative velocities and so on. And this is very, very messy. So that's why I prefer to use the centers. And in general, the center ones are much more precise. So now we can solve with Runge-Kutta. And you see, I'm just solving these two because we know that the other is going to be I know what's going on here. So I solve here, I get two solutions for the center derivative for the plus, and I'm using the Runge-Kutta. You see the convenience of using this is that here I have just to put which is the method I want to use and just use it. And here I'm using that the delta t is fixed to delta t, and I'm not doing adaptivity. Adaptivity means that the code, these libraries can check for some, check the equation, and if the equation doesn't need to have a dt so small, they will make a dt larger, or otherwise, if the dt is too large, they will be smaller. So we don't want the dt to change, so we put this false here, because we are, in general we can leave it, but for this proof it's better to have the dt fixed, so that we know how much it is. And here are the solutions for one time step. And let me compare with the here is one. This tries to fill with whatever he likes. Here we have in red the initial data, in blue the not solution, the center difference, and in green the one which d plus. And you see here now Runge-Kutta is not Euler, so we won't be solving exactly the equation, and we see that there is a lot of dissipation with this method. That's because we saw that the eigenvalues of t plus have a negative real part, so we see here how important is that negative real part. We have a lot of suppression. The solution is less than half of it. And we have the blue here. This is the approximation we are computing now for this delta x, delta t. Of course, if we take delta x smaller and delta t smaller, we will get closer. But we are going to see later on how to use higher order methods which are much better. So this is just the expectations that we have. So we have more error in the d naught than d plus, but because this algorithm was exact, and the d plus has more error in this case than the d naught, because in Runge-Kutta we just are not solving the exact system, and we see this. So now we will put some high frequency in the solution. So we take omega equal to 25, and this is the initial condition then. So we see these are the data points, and we see that there is a lot of oscillation which are not very well represented, right? But this is going to appear in the simulation because that corresponds to error, say. So this is an initial condition, which is, you might think, okay, it's just some error, and then we evolve them. We just evolve up to t 0.25, so 1/4 of the period, and with Runge-Kutta 4, and this initial data is mid-frequency, we call it. It's defined here with a mid-frequency. And let's see what happens. This is the initial condition in dashed lines, red, and this is solution after 0.25. So the solution should be, the exact solution of that should be around here, because it's moving, well, a bit less than that. Should be centered here, so it should be like here. Nevertheless, it's here, it doesn't move, does not move. If you remember, this is because the phase velocity of a wave and the group velocity also has some zeros for high enough frequency, and this is one case. You see the solution doesn't move. If it doesn't move, means that when you compute the f is almost zero. It has decreased a bit, but it's in the same place. So you see how this noise behaves like now. It doesn't propagate, stays at some place. And this is pretty bad, because if you are solving some nonlinear problem, you might get something that stays in a point, and because the nonlinearities can start growing. In another case, it will just move away, but if it stay at rest, it can start growing, growing and growing. So this sometimes is very bad, so one have to be careful with this. That's why I mention and I simulate here. Okay, let's try another one. Now we can double the frequency and go to omega equal to 50. So this is the initial data. So it follows the line, but in one point is positive and the other is negative, and we evolve also for 1/4 of a period, and now we get this, and you see you still expected the solution to be around here, but it's on the other side. The solution have moved toward the right and not towards the left. And this is because the group velocity for this high frequency is negative. Remember, I'm going to show you later on the plots we have the other day. So this is the group velocity that makes this thing moves to the right instead of to the left. And this is also source of all kind of inconvenience when one does simulations, right? So high frequency, where things are not well represented, should not be allowed in the calculation, because they do very strange things. We know which things do, so we can check what is going on and understand what the solution is doing, but it's far from the real solution. So here, to understand all these things, here we compute the eigenvectors, eigenvalues for finite difference operators. Remember we did the other day for the continuum derivative operator, it's just the eigenvectors are e to the I 2 pi kx for whatever k is, and the eigenvalue is this negative, imaginary value, I 2 pi k. And so if we plot in k, this is just a line, 2 pi times this line. Okay, so we have a straight line. Thus the dispersion relation is constant. So because the dispersion relation is you divide by the velocity, you divide by k, the constant velocity, when you are solving the system. So these are the eigenvalues, and now you do the same for the grid. And in the grid you have two things. First, you want things that are periodic, so you require that when you move a distance L here in X, you get the same point, so this should be proportional to some n times 2 pi I. So that fixes the case. The case has to be n over L, where n is some integer and L is the distance. So you have this relation, right? And also notice that if you take n too big here, k is n over L. If you take n too big, what will happen is that you will go all over the things will go up to the first factor, right? The n will be, for n big enough, you will get to the same value that has the function before. So the number of functions here in the grid is finite. So we have this relation, that XL is just this, which you can write like that, and so this is an integer. So the actual kns that you can take, which are independent, is this one with n going from minus n over 2 to n over 2. You can shift this if you want. You can do from 0 to n, but this is a customary thing. Choice of the basis. So we do the same calculation as the other day. We say, okay, the d plus, d minus apply to this at the point L is this, which has L plus 1 here and XL here, and you write down what this is and use factor this factor. So this is the eigenvector, and the eigenvalue comes from here and is this one. And from the center difference, you have to average these two values, and when you average these two values, this goes away and you get this factor here. So the eigenvalues are purely imaginary and have this form. And here we computed the eigenvalues for the center difference operator. This is the D2 and this is D4, all are imaginary, purely imaginary. the 6th and the 8th. So this operator is, say, is the one that has an error that goes like delta x to the 8th. So it will be exact up to polynomials of order 9. And you see that in the middle, they are like here in the middle, they behave very nicely like the one for the continuum spectrum. But further away with the wave numbers, they will behave pretty badly. Huh? And they go to 0. So in general, you try to do your calculations with wave numbers that are in this region. And if you use a bigger operator, you can say for this, for instance, for the 8th, you can take waves up to here, say. So going high in the derivative allows you to, in the precision, it allows you to go to higher frequencies and represent them. Okay. Okay, let's stop now let's continue at 10:15. So this is a good point to stop. Questions? Oh, you mean in the adaptive? In this, let me go back. Where we are using adaptive here, adaptive equal to false. This thing? Yeah, that means that in this library, most of the methods have some adaptivity. That means if they try to preserve some error, and if they see that you are making too much error, so that the f is going to, if it's growing too much, they will take dt smaller. So dt of n plus 1 will be smaller. And otherwise, if this gets too small, then they will take a bigger. Usually, this thing is done like dt n plus 1 is dt n over 2, and they will try, or the other way around. So that we don't want here, because we really want to see what is the effect of pure Euler or pure Runge-Kutta. So that's why we put adaptivity. And also for the Q factor, when we compute the Q factor, we don't want to have this, because that will spoil everything, because at every time step the dt will be different. So we try to, for studying the method, we try this. We always put this. When we are running for getting a real solution in a real problem, we might, after computing the Q and finding out how the system behaves, we might just release this and leave that the adaptivity start working, and this is okay. But for the moment, we cut it, because it can create problems. For instance, we know that we were talking about this stability region, right? Say for Runge-Kutta, it's something like this. And at some point, when you are using this, if they try to use a dt too big, it will go here, and then the system is going to be unstable, and maybe it will try to even go from here to here, etc., and that will spoil all the solutions. So we just take constant, because for our problems this is okay. For some nonlinear problems it's good to use it, but not for this. Okay? Okay. So we stop and continue at 10:15. Okay. Okay, we continue. Can you hear me? Okay, thank you. So we continue. So we are going to use now, let me remember what I was doing here. So we have these problems, we have the eigenvalues, eigenvectors. This is the dispersion relation. And so we apply it. Since we have the eigenvalues, eigenvector of the system, we can write any solution we are seeking as a B, which is some constant times the base, right? This is e to the I 2 pi, etc. And so the points in the grid are this one here, where Kn is n over L. And we have the XL here. And if we take the time derivative here, we use the equation, and we use that the d of E is equals to lambda n En, right? Then we get this, the system becomes just this simple system for each of the modes. And applying the center difference, for instance, we get this. So this we can solve, and this is the Wnt is the exponential of t, right, of this, all this thing here, times t, by the value at 0, and the value at 0 when we now get the position in space also. This is the L here. We get this, here there is the XL, okay? We have here the T dependence and the L dependence. So the solution we are getting is a continuous function here, which is this one. So we have a wave traveling at this speed now. And this is so it's A times the dispersion relation that we find, okay? So this thing here, this term here tends to 1 when dx goes to 0, right? Because sine of x over x tends to 1 when x goes to 0. So we get to the correct dispersion relations. We get the velocity to be 1, right? But for dx equal to 0. Otherwise, we have this factor here, which is the one that we plot upstairs. It's the one we plot here. So this divided by k is the speed. I think I have the plot here. Yeah, I think I have the plot here. These are the phase velocities. You see near 0, the velocities are near 1 for low frequencies. But then when the frequencies grow, the D2 is pretty bad. But you can see that these ones, D8, D6 are very bad, very good. You can keep up to frequencies of order, say 18 or so on each side is good. The fourth order is only good for, say, up to 5. So these other two are much better. But they have their problems also. What is the problem is that if we look at the group velocity, namely the derivative of the, here we are looking at lambda k over k, right? This is the velocity, the phase velocity. The group velocity is this one here. This one. And so when we compute it, for instance, for this case, give us this. And we'll see how it behaves. I think that there is a mistake in this formula. I have to check. So we plot here the group velocities. And you see how they behave. The D2 goes from 1 to -1. This is what we saw. But for high frequency, we have the wave going into the other direction. That was this point here. And here was a 0 that we saw at half the frequency. So this was a plot where the solution didn't move, and this one was the one that moved in the opposite direction. But notice this one, for instance, the D8 has a very large group velocity in the negative direction. In both, these are symmetric, so it's the same. So one have to be very careful with that, because things move very fast on the grid, go away, the noise can travel very fast, and so you can get here very easily. So in general we try to kill all this, so we try to get frequencies only in this part. The rest is just not represented. It's bad. So we try wherever we have noise in this region, we try to eliminate it. And this is what we are going to do next. So we introduce some dissipation. The idea of the dissipation is to use some operators of high order. So in a sense, it's like to make a heat equation, right? So you have for instance, you have this equation, and now you add something with some constant here with delta U, Laplacian. So this will create a negative real part for the eigenvalues, and that will suppress things. And this is going to try to suppress higher frequencies, like, because this is going to behave like a heat equation for this. So if you have something of high frequency, will try to smooth it away. And since you don't want to change the character of the equation, you might put here some delta x here. Right. So so let me put it better here. So you might try something like delta x here times k times Laplacian u. Maybe delta x squared, for instance. So when you try this thing, when delta x goes to 0, this part goes to 0, and you don't see it, but it will nevertheless kill the high frequencies. So the Kreis-Oliger operators are generalizations of this, where you put here a higher frequency, a higher power. For instance, the Laplacian you can approximate by d plus, d minus. So here this is the Laplacian to the p. So Laplacian to the p is d plus to the p, d minus to the p. So this here is Laplacian to the p times delta x to the p. And you put this factor here, for just making that the eigenvalues of these are close to the unity. They are real, they are negative, and they are close to unity. So here you compute, for instance, the eigenvalue of this. You see that these are these things here. And here I made a plot of them. How they behave with frequency. And you see for low frequencies they don't do anything, almost. I mean, the second order is pretty bad, but the other ones are very nice. For high frequencies, frequency up to here, say, they don't do much, but they kill all the high frequencies. Here this is a negative, the negative real part, so this number is very big, negative, so these things are killed almost immediately. So you get a solution which just has frequencies in this range. So how do we use them? Oh, I have a mistake here. Well, you can see that the Kreis-Oliger was something like delta x to the p, and the derivative is like the Laplacian to the p, right? So this thing applied to a smooth function will be like delta x to the p times the value of this of the derivative 2p derivative of u. So if this is a nice function with bounded derivatives, this is going to go to 0 like delta x to the p. So this combination here, delta p to minus k to p, this combination has an error. So this term here goes like delta x to the p, and this has an error of delta x to the p. So this is a good representation of the derivative plus delta x to the p times sin c. So this is very good. So this doesn't change the accuracy of this operator. It just kills all the high frequency. So this is very good. You have everything you want. You have a very accurate operator for smooth things, and it kills everything that has high frequencies. So this is for smoothing. So if you want to treat shocks with this, it's not good, right? Because this is going to blow like crazy. So this is good when you don't have shocks, when you have a smooth solution. But there it works very well. So now we are going to try it, and now we are going to use this other library which is called summation by parts operators, and that has all these finite differences you can dream of. So we are having n equal to 100, l equal to 1 as before, and this is a second order operator, the center difference, and I'm going to call the 2 periodic here, so to distinguish the other one we made, which is the same, but just in these libraries I'll put another name of it. So it's a first derivative, that's the order of the derivative. The accuracy is second order, and it's between 0 and L, and has n points, and is periodic. And associated to this one, we have this dissipation operator associated with the 2 periodic, right? So this will be with p equal to 2, the Craig-Sollier. And we can run this, and we can see the Craig-Sollier operator, for instance, and this thing here. I'm sorry, this is the derivative operator. Here appears with 1 over delta x, that's why these numbers are big. And you can also check the form of the other one. This is the Craig-Sollier, which you see is much smaller in size than the other. So we have these 2 operators now, and then we are going to create a function that is as before here with omega equal to 0, this omega 0, and we are going to add some noise. So we multiply it by this factor here. So it's a noise that is around here and has a frequency of 50. So this is the initial condition, so it's very noisy over something smooth. And we now evolve with this. And you see here, you have the solution, the initial condition in red. Without the Craig-Sollier, you have all this noise here, still. But when you put the Craig-Sollier operator, you get the green one. So it has killed all the high frequency. And if you run to 1, but let's say we run to 0.5, 0.25 say, and then we can see the smooth part goes to the left as it should, like the good solution, while the noise goes to, you see, when you do without the Craig-Sollier dissipation, you have this big noise here in blue here, so all this part of the solution is moving this way, and when you put the Craig-Sollier, it is smaller, still present. You can see here small, but it's much smaller. And then if you run later, as we did just to 1, we see that the noise in this, for the green line, it has disappeared. So there is nothing here. So crazily is a nice way of killing all the high frequency. Okay, what happens if you have a smooth solution, or you smooth it out with the crazily and have to have more precision? Let's first do the following. Instead of solving up to 1, let's solve the problem with the second order center difference, but up to t equal to 10. And here I'm using a very high order Runge-Kutta, which is 8th order. That's why I don't want to have the error from the Runge-Kutta also. So I just use for everything now a very powerful Runge-Kutta integrator, very precise. So we see up to 10, when we run up to 10, the nice solution with second order is pretty bad. It's really, has really been deformed totally. So it's of no use. So what happens if we want to run things for a longer time period? Well, we have to improve on the methods. So here I'm not sure I define these things here. Let me check. If I define these things, I'm missing some. I think I'm missing one of these cells here. Okay. I define derivative operators of higher order. The same as before, periodic derivative operator, order 1, and I put accuracy 4, 6, and 8. So now we have all the matrices for these operators. Let's see, let's check. Let's check the D4 that we have computed by hand. Oh, I got a markdown cell. I'll change it to Julia. And you see, for instance, in this point, I have 8.333 minus 66 here, 0. This is the second point. I mean, a star like this, it has this other, and then they have the plus and the plus 8 and minus 8, which is this one. These are the 4 numbers. So I run them. I create the problems and put names. So this is the name of the Runge-Kutta integrator, and this is the order of the finite difference for every solution. I create all this and run and I plot. And here is the solution. You see with 10 periods, and you see that these ones are very good. The D4, D6, D8 are very good. In fact, the D6 and D8 don't have much difference with the real solution. The initial condition is in red, dashed red, and you see that it's overimposed. You can, if you want to distinguish between them, you can go and run for 100, say. This I don't have to change, but and you see for 100 already the D4 is quite deformed, but the other tools, the D6 and D8 are still very good. And if you want to distinguish them further, you can run to 1,000, say. And there you see that already the D6 has an error, but the D8 is very, very good, and the D4 is pretty bad. So you see, if you want to run for things for long times, you better use some higher accuracy method. So I put some exercise here I can make, and now let's finish this part with the error propagation. So we know that we can compute the Q factor. Which is the difference. You do 3 calculations at different resolutions. B with dx dt, B with dx over 2, dt over 2, and so on. You can also do, for instance, fix a dt very good, very large, very small, like dt over 4, and do all these 4 calculations with dt over 4. And so you will see all the error in dx. Or you can do the other way around, fix the dx and change the dt, and get how the error behaves on dt. So we'll check this with the Q here. We just take, since we are taking the solution, we have to use some norm here. Actually, I will put some norms here. Some norms here. Some norms here. Now, oh, okay. So we have to take some norms. So here we take just the Euclidean norm. So this different, this prime makes this the vector to be from vertical to horizontal. So we can make product of matrices. This is a vertical matrix, this is a horizontal matrix. So it's like the scalar product. And we take the square root after. So you use 3 resolutions, 80 point, 160 point, 320 points, L equal to 1, T equal to 1, just one period. Here we make the dt's and the x, and the x1, x2, x3. We make the initial data for the 3 resolutions. We use a bump with 0 frequency, so it's a nice smooth bump. We create the periodic derivative operator with this number of points. we create the parameters, we create the problems, we solve the problems with the shift. Here you can solve with rungecuta, and then we compute the Q at the end, this value here, and then we plot the Q for all times. So here is a check that x1 n is the same as if you take x2, which is a higher resolution from x1. If you take the points in between, they are the same, and they are the same of this. So let me plot this. What we are doing is having this point 1 in the slow. No, I need to get it further away. Let's say I have a point 1, 2, 3 in the lower resolution. Then in the mid resolution I will have another point here and another point here. So in this intermediate I have 1 here, 2 here, 3 here, 4 here, 5 here, and then I have another one, which are these ones. So here, here, everywhere here. So this is a 1, 2, 3, 4, 5, 6, 7, and so on. So if we look at this point, which is a 2 in the coarse grid, it is associated with the third point in the mid grid, and the fifth point in the high resolution. So here it says that, okay, the point 2 here, which is the second point here, is equal to the second point here, which is 1 plus 2 is 3, and is the second point here, the fifth point here, which is 1 plus 4, which is 5. So that checks that every point is okay. And here we compute the Q factor and we get almost 4. Remember that for a method that is second order in space, we should get 2 to the 2, so that's 4, so it's more or less okay. And here is how it behaves. It starts close to 4, and then while the simulation is running, it goes down a bit. And this is because there is not only this error. Here we are measuring the error in the delta x, but also we have in the error in the integration, etc. And so it's not quite 4, but it's diminishing. So, but you can see that it's close to 4. So the method is second order in space. So finally we are going to see something else, which is energy conservation, just to track conserved quantities, right? In our equation we have in the continuum, we have this energy U square is conserved. Here we have a proof that is conserved. You take the time derivative, put the time derivative inside. That means that this is twice u times the time derivative of u. Here you use the equation to replace dt of u by a dx of u, and you put this 2u dx of u as the total derivative of u squared, and so this is equal to A times the difference between U at the endpoint at the beginning, and this, since we are in a periodic situation, this is 0. So the energy is conserved at the at the continuum, and we have a a similar energy for the discrete, which is just the sum of the points times dx. The dx doesn't do anything here, but I just put it to keep the sizes and the lengths correct, the dimensions correct. So here we do the same. We take the time derivative of this. This is okay. I can put the derivative inside. So I get this. I use the equation and I get this. And notice that this is 0 because this is this matrix applied to B and applied to B, right? And sum. So this thing is 0 because this metric is anti-symmetric directly. So I get 0. So what is here is B D not B, right? And this metric is symmetric. Are there some questions or something? So I have a exactly conserved quantity at the semi-discrete level, right? Semi-discrete because here we are using the equation dt of bi equals to a d0 of bi, right? So it's discrete in space and continuous in time. So at this level is this energy is conserved. What happens when we discretize also in time? Well, we can compute this. So we define this energy function, which takes a solution and dx and produce this thing here. We take 1,000 points, 1,000 periods, and solve the problem. And now we plot the energy here, and we see a decay, a small decay, right? Look at this, is only in this figure, right? It goes, so it's almost constant for a factor 1,000 or so, or 10,000. So this is this decay, and this decay is because when we look at the stability region, we say something like that, but sometimes we are inside these points. Sometimes we are here, say, with some of the eigenvalues, and this here is the function. The stability norm is 1, the stability indicator. Inside here is less than 1, and outside is bigger than 1. But since we are here, the stability factor, the amplification factor, is less than 1, and so we expect that if we run this eigenvalue for a while, that we'll get a something decreasing, and this is what we see here. It's very small in any case, but it's present. So I made this with the Runge-Kutta, I think. Yeah, with the Runge-Kutta 4. So it is precisely this plot. So we have some decay. This is a numerical decay due to the time integration. It's there, exists, but it's usually very small. But we can check. Here there is a homework that says, okay, take more points and see what is decay. this decay we see here is linear, but actually it's an exponential. If you take more periods, you will see that this becomes to be an exponential, and you can compute the exponent of the exponential and see what is the decay constant. And then I put some other exercise here. Just take an A that depends on X, and for instance take something which is positive here and goes negative here, so no, the other way around. I want the other way around. Negative here, so this is a wave that moves that way, and then you make it positive here. So in this side there is a wave coming like that, in this side like this. So you put something and see, and here is standing. Here you can see what happens with the solutions, and you can see what happens with the noise, and use Kreisoliger to see what's going on here, etc. And you have to make it periodic. So here you do some part like this. So you make the A periodic like this. And so here you will see a region where things want to accumulate, and a region where things wants to go away. But for the noise, it's the other way around. For the noise wants to be here, and the solution, the smooth part, wants to be here. So you can try Kreisoliger, play a lot. If you want to understand this, it's good to play. And try to guess what you get. Before evolving, try to guess what you will get. This is the best way of learning this. So I'll stop here and we continue in 15 minutes. Now we are going to discuss, actually Pablo, we are going to discuss lab 1 to see how to do it, etc. And if there are questions, things, we will concentrate for a while in the lab 1, and then I continue. Okay? So in 11:15 we'll continue. Unless there are questions now about this, I finish this now. So if there are questions, this is the moment. ¿Qué cosa? ¿Los gráficos? Los gráficos. Ahora lo vemos. Okay, let's stop for until 11:15. Huh?